Okay, a new little project I'm going to have a play with. When we cut materials, particularly on the lathe and the milling machine, we always hear about surface speed or cutting speed. You know, what you're supposed to be, the recommended speeds for cutting certain things. And I like to sort of know what speeds I'm cutting at, and it's good so you can replicate it. If something, a certain tool you're using is working out particularly good at a certain speed, it's nice to be able to throw that back at the machine at another time and hopefully experience the same results. So I happen to have a tachometer from years gone by. Only works in RPM, and there is no surface speed, surface feet per minute. I think this was actually made in the USA, Illinois, Skokie. There we go, Skokie, Illinois. Power Instruments Incorporated. Tachometer. Works quite fine. Only thing that that is a problem with it is that I don't have a surface speed wheel. Apparently, is it here? I'm pretty sure I didn't show that on camera. So this is the tachometer that I have. Why make it redundant and not use it if it's perfectly fine, except it doesn't do surface speed, surface feet. Surface speed? No, I was right first time. So what I want to do is make up a little wheel for measuring surface speed. So this is an idea that I did get from watching one of Mr. Pete's videos. Great treasure trove of information that he has given us all in the YouTube and machining community. Thanks, Mr. Pete, absolutely. So this is the little manual that came with a device, and right at the back here it mentions about optional speed measuring wheels. It gave me a bit of an idea. I mean, I've not always the brightest tool in the shed, but it actually dawned on me how they're working out RPM on this machine to surface speed. With the wheel, they are saying for in metric, they say a 10 centimetre circumference. So that means that every RPM, the surface that is pushing the RPM round, if that makes any sense, would be travelled 10 centimetres. And a similar one here they have in an imperial version. You've got a 6-inch or half foot circumference. So for every RPM of a 6-inch circumference wheel, it's moved half a foot. And so you can just do a factor of whatever it would be, which in this case, half a foot to get into foot would be dividing it by 2. Yes, divide it by 2. If the RPM is showing 100 RPM, well then it's actually travelling at 50 foot per minute. So I've decided, I thought I had the correct O-ring that I'd ordered. This guy here. And I was going to do the metric side of it, so I was going to make the 10 centimetre circumference one. Well, I ballsed up. And what I ended up doing is getting an O-ring that's a bit too big. So if we go to our little drawing of what the O-ring itself ended up being, 28mm ID or 1.1023 inches and a 34.8mm OD. Now that was too big. So what I decided to do was wing it and just make another wheel and use a different fudge factor. All I have to do is basically come up with a factor to times or divide the RPM by. Hence this little bit of calculations here. So how I worked it out is I'm going to go with the imperial side, 100 feet in feet per minute. So basically to cut steel, 100 feet per minute is always sort of mentioned. So as an example, 100 feet per minute is 1200 inches per minute, because there's 12 inches to a foot, and so times it by 100, there's your 1200. That would mean what I've got to come up with is this O-ring, a use for this O-ring. So with this O-ring, its natural state, as in it is sitting there doing nothing, the OD is 1.5031 inches. Obviously, it can't be sitting in space, it has to go onto something. So whatever it slides onto needs to be able to hold it. We need to actually make this dimension across here bigger. So I fiddled around with the sums and the sizes, so that if we make this outside diameter when it's on an arbor to be 1.591 inches, that gives it a circumference of 5.002 inches. So every time this tachometer registers 1 RPM, it has moved 5 inches of surface speed. Okay, so if we use our example of 1200 inches a minute as 100 feet per minute, you would divide that by 5, because every RPM around this, when it's on a mandrel, will be 5 inches. So when this tachometer registers 240 RPM, we are now travelling at a surface speed of 100 feet per minute. So, continuing the example on, to test it, if we wanted 75 feet per minute, there's a relationship between this 240 and the 100 feet per minute. And that relationship, as you possibly can see, is 2.4. So, if we divide 240 RPM by 100, you end up with 2.4. So let's test this. If we wanted a 75 feet per minute setting, to work out the RPM of that, you know that 2.4 RPM is required to maintain 1 foot. Because 1 foot, 2.4 RPM, 100 feet, 240 RPM. Therefore, if we times the 75 by 2.4, we ended up with 180 RPM. To check this, we can reverse our measurements. So if we had 180 RPM and we know 75 feet per minute is 900 inches, then you go 180 into 900 equals 5 inches per revolution, which we know that is the outside diameter of our inch of our rubber tyre, our O-ring. And then I thought to myself, well, what if there was 297, let's just throw that number in there, 297 inches per minute, 297 RPM was showing on the tachometer. What's that in foot surface speed? So 297 divided by our 2.4 fudge factor, which we've already used here, would mean if the tachometer was showing 297 RPM, that would equal 123.75 feet per minute. Then I got to thinking, 2.4 is our fudge factor. Yeah, you're probably going to remember that, but what would it take to change this to something a little bit easier to remember and still within the capabilities of this O-ring? There's no point trying to stretch that to 3 or 4 or something and have the O-ring so deformed and it's stretched that it's probably going to break after a couple months. So what about 2.5? I need to back engineer this slightly to see what the original diameter of our O-ring when it's on the mandrel needs to be. At the moment we're going to have a 5 inches circumference, 1.591 diameter equals that circumference. So in this little problem we've got down here, what if the fudge factor instead of 2.4 was 2.5? We go 75 times 2.5. That would mean if there was 187.5 RPM noted on the tachometer, that would have a fudge factor of 2.5. Now, what would that equal in the circumference that was needed to achieve that? Because you can't change that without changing the circumference. Now, we know that 75 feet per minute is 900 inches. If we did the old 900 divided by 187.5, we end up with 4.8 inches. So if I change this to 4.8 inches, we can use a fudge factor of 2.5 to work out the diameter required. To determine diameter of the circumference of something, you divide it by pi. So as we all learned in school, pi d. So pi times diameter equals circumference. So if you know the circumference, then you divide it by pi. So pi is 22 divided by 7, which I'd already thrown in my calculator to get a really accurate pi. I always remember it's 3.142 something, but let's do it properly. So if I divide that by our memory recall of 3.142857142, and I've had enough, that equals 1.5272 repeating diameter. I'm going to change that diameter to 1.5272, 1.5272. So we've actually gone down a little bit on the diameter. So when this O-ring is, I've got a bit of Delrin here, which just so happens to be nearly perfect for this. I can squeeze this O-ring. So squeeze, it's a 35mm. I know I'm mixing my inches and metric, but that's just the way it is. So she'll go on there with a little bit of effort, so it's a bit tight. But I will be able to take a little bit of pressure off because this is going to be a smaller number. So the diameter is going to be smaller, so you can definitely sit over this. I think this gives me a diameter of about 41.2 millimeters. So let's just go back to inches. 2 divided by 25.4. So we've got 1.622 inches is what this sitting on here currently is at. So because we need to go down to 1.52, bit of a groove in here would bring us down to a nicer number, at least for this O-ring, so it's not suffering as much stretch. And so the next thing I'm going to have to do, I think I used to use this for threading, external threading on this high-speed steel. I've gone to inserts and stuff now, so I might just change the nose on this a little bit to give us a nice little seat for this O-ring to sit in, and go from there. And then I have to make up an arbor. The arbor is probably going to be trickier because you see how this works here. Get some stuff out of the way. Probably overhead camera's the only one that's going to see this. This little piece here is quite thin, so it needs to expand to go over the top. So I need to nut that out so that it'll go on there without too much force and not be too loose. Putting those slots in there will be interesting. No way I can do a slot that skinny, but we'll see. See what I come up with. I might just aim for a really nice fit without having to be using the slots for expansion. Remembering that this wheel is reasonably big in relation to this. I mean, I think this can go up to 9,900 RPM. Well, there's no way with a bigger wheel. As I said, what are we doing? 100 foot per minute is only 240 RPM on this, so it's not like this is going to be whizzing at 1,000,000 kilometres an hour. Or miles an hour even. Okay, over and out.